Hey everybody, and welcome to Linear Algebra Online. So I want to talk today about a very important proof technique called mathematical induction. So I want to motivate this with another matrix multiplication problem. So if you do a squared, a cubed, a to the fourth, so on with this a, all right, you're going to get a squared is 2 basically all twos. A cubed is all fours, and a to the fourth is all eights. And a lot of times you run into like these patterns when you're doing like matrix multiplication, and there's actually a geometric meaning behind why we're running into patterns, and we'll actually talk about those kind of things too. But there is like a lot of things in math where you see these patterns and you start to try to make a prediction as to what like a to the maybe n would be. And in this case, it actually does work out that a to the n equals 2 to the n minus 1, 2 to the n minus 1, and 2 to the n minus 1, 2 to the n minus 1. You can actually go and plug in, 2 for n, and you get 2 to the first, 2 to the first, 2 to the first, 2 to the first. If you plug in 4, right, you're going to get 2 cubed, 2 cubed, 2 cubed, 2 cubed, so on. And a lot of problems, not even just in linear algebra, but a lot of problems in math and science, you observe like a pattern like this, and then the way you actually prove that these patterns work when they're like to some nth power, like on the natural numbers, like the counting numbers like this, is you need this idea of induction. And induction is like a technique it's a proof technique basically used to prove some pattern holds like for the natural numbers. And basically today, it's not going to actually look like a lot of linear algebra because I really just want to go through and show you how this mathematical induction process works. That's the plan. So the way I honestly think about it always is dominoes. And dominoes really are like the perfect example for how this mathematical induction thing works. So again, we're going to always just use this with the natural numbers. So when we talk about induction, just think naturals, okay? And the idea is, if you were going to knock down a bunch of dominoes, right, you need to get the domino started, assuming no wind and things like that, right? You basically push the first domino, and that's what we think of as the base case. So we basically mathematically, like by hand, prove that the first natural number, n equals 1, works. Sometimes actually we do this for natural numbers and 0, which is technically called the whole numbers. But let's just say like the first case, whatever that really is. So we have to show that n equals 1 works. Whatever pattern, we have, we want to mathematically show by hand that it fits the pattern. Okay, like we would show, this a to the first would really be, the first pattern, and you would just take this and you'd be like, hey, look, a to the first is 2 to the 0, 2 to the 0, 2 to the 0, 2 to the 0, and that's all good, right? That would be the base case. Then the inductive hypothesis is where we're actually going to assume that the pattern holds for some k, which is less than or equal to n, the last one in the cycle or in the pattern. And then we assume that it holds. Basically the idea there with dominoes is we assume that if we knock one domino down, then it knocks the next one down. So we can let k be anywhere in this, chunk of dominoes. And the idea is just anywhere we're at, we assume that the pattern, the kth one, knocks down the k plus 1 1. And so basically the pattern just holds for somewhere in that cycle, okay? And then the inductive step is that we're going to, just trying to think of what color I want. So we're going to use K, the assumption from the hypothesis up in step 2, and show that K plus 1 follows, all right? So we're going to do a proof where we assume K and show K plus 1 follows. And the idea is if we, start off and you have your domino and we push that domino down, this is like the first one and this is the second one. We do this in our base case. Then if we, we can think of the kth case as being, this K equaling 2. And if we've shown that K implies K plus 1, then that's going to imply that the third one gets knocked down, right? But now I can think, well, K is like arbitrary, so K could also be this one, right? And so then it could knock down the fourth one, and so on and so on and so on. So then you basically get it, so all the dominoes will fall down. That's the idea. And I think it's best if we just go through a few examples with kind of basic number ones first before we jump into induction with matrices. So let's just get into it. So this is a very famous pattern with odds, okay? And if you've never seen it, I just got the first few here, and hopefully it's enough to see the pattern. But 1 equals 1, brilliant statement. 1 plus 3 is 4, okay? 1 plus 3 plus 5, 9. 1 plus 3 plus 5 plus 7, 16. So basically, as I'm adding these odd numbers, right, like successive odd numbers, I'm getting perfect squares. And this is actually like the way this worked, and like when people first figure this out is like they see a pattern and then they're like, oh, I wonder if I add all, if I add all these up to, 2 to the n minus 1, like odd, like an arbitrary odd, does that equal like that number squared? And to prove these patterns, you need that induction thing. And so I'm going to go through, these are called the square numbers because of this. But I'm going to actually go through like the formal proof on the next page. But basically the idea of how a lot of these will go, you might run into a pattern this year and you have to create this. And this is very much like what like a lot of research in math and science feels like. You come up with this theory and this hypothesis, and then you use a technical thing like induction to actually prove that that pattern holds. So let's do it for this. And I thought I'd also kind of show you this picture. So this picture is showing you actually like visually how this works. So if you take, this right here, let me maybe color code this a little more. So this is my first odd number 1, okay? That would make a square, like a 1 by 1 square. Then if I add to it the next chunk of odd numbers, right, these 3 right here, then I get a 2 by 2 square. So that's like, this line, 1 plus 3 is 4. And then the next one out, if I add 1, 2, 3, 4, 5 more, next odd number, right, I get a 3 by 3. I get 9, right? 1 plus 3 plus 5 is 9. And you can keep doing that. You can add, I'll just do one more here. So we've got, 1 plus 3 plus 5, and then plus 7. I had trouble thinking of the next number for a second. But this one would truly be 4 squared is 16. And these are just called the square numbers because of that. It's just kind of a weird property. But this is how you would formally go about writing up this proof. So I'm going to write the base case first. So base case is just showing that the first, like you basically are knocking down the first domino. So 1 equals 1 squared. Yep, that works. Done. Okay. So now I'm going to assume that 1 plus 3 plus dot 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 plus 2 to the k minus 1 equals k squared. So k is like inside my 1 to n list of numbers, basically. And I'm going to assume that holds, all right? And I'm going to show that 1 plus 3 plus blah, 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 2 to the, maybe I'll even write, I'll write this one. And so if you, the next odd number would be the 2 to the k minus 1 plus 2, right? Which is 2 to the k plus 1, right? So that's the next odd after 2 to the k minus 1. And I have to show that that equals k plus 1 squared. That's the inductive hypothesis. So I have this to work with, and I need to show this. All right? And basically the way these a lot of times feel is if you want to show this equation holds, you can work with that part, and you just need to, do some manipulation with algebra and get to this, okay? So I know that 1 plus 3 plus dot, 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 plus 2 to the k minus 1 plus 2 to the k plus 1 equals k squared plus 2 to the k plus 1 by my inductive hypothesis. And that's just because, all I did was substitution. I took this part, and it's k squared right there, right? So that was my thing I had to work with. So then I'm just going to say something like, note k squared plus 2 to the k plus 1 equals k plus 1 squared. It factors into a perfect square. So this proves that 1 plus 3 plus 5 plus blah, 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 2 to the n minus 1 equals n squared, holds for all n in the naturals. And that's it. So you knock the first domino down, you assume k holds, and we're going to show k plus 1, and there's always a step where you insert the hypothesis part right here. And then you just do a little bit, in this one, you just say oh, look, that thing factors. And so that's it. I just have 2 more examples that I want to do. And one of them is pretty similar to the one we just did, but this one's kind of different. So I think it's a good one to see. So you can do some clever kind of inequality work on this one, so I think it's kind of good to see it. So I'm going to prove that n factorial is greater than 2 to the n for all integers greater than or equal to 4. So, really that still applies to the naturals, so it's going to work here. So the base case is just n equals 4 because it's greater than or equal to 4. So you don't need to start at 1 here because the problem says specifically greater than or equal to 4. So you can just say, note, a lot of times these steps are really straightforward. 4 factorial, which I should go look it up. Hold on. Just to make sure that I don't get it wrong. But it's just 24. Note that thing is greater than 2 to the 4th, which is 16, right? And so that is the base case. You basically just knock down the first domino. And then the assumption is that I'm going to assume that k factorial is greater than 2 to the k, like holds for, I guess I can use that little symbol, holds for all k greater than or equal to 4. And we will show that k plus 1 factorial is greater than 2 to the k plus 1. Okay? And if we do this, then we've really shown it for all of them because we've gotten that chain of dominoes to keep going. So this is basically, I just realized I wrote a squared there. I don't want a square there. I want that. So same kind of structure as the last one. I'm going to start with this, and I'm going to arrive at this. So k plus 1 factorial is equal to, just by definition, k plus 1 times k factorial, right? Because it's just like k plus 1 times k minus 1, blah, 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 blah. So that's just the definition of k plus 1 factorial. And, you know, this is greater than k plus 1 times 2 to the k by our assumption. Right? That was exactly what I'm just using, you know, this part right here, k factorial bigger than 2 to the k, right? Then, since k is bigger than or equal to 4, I could also say that, just note k plus 1 times 2 to the k is greater than or equal to 5, because k, you know, at least could be 4. So 4 plus 1, 5, times 2 to the k, which is greater than 2, right? 5 is bigger than 2, times 2 to the k, which is equal to 2 to the k plus 1. And so if you trace this through, you know, this shows k plus 1 factorial is bigger than 2 to the k plus 1. So using induction, we've shown that n factorial is greater than 2 to the n for all n, whoops, I was about to write naturals, for all n greater than or equal to 4. And that's it. So kind of a different problem, but similar kind of structure. All right, I just want to do one more. It's another really famous one, and is one that you can actually visualize pretty well. So if you add up the first n naturals, it equals n times n plus 1, all divided by 2. And you can visually kind of get a sense of this pretty quick. So here's my first n naturals, right? And if you add to it n plus 1, okay? So notice, if you add to it n plus 1, you basically make this grid. This is an n by n plus 1 rectangle. And so if you could cut on that diagonal, half of it would be the sum that I'm talking about. That's the idea. So it's like you take this and you flip it around, glue it, and because of how it glues, right, there's always 1 plus n, so n plus 1, but this is n. So then you get this square, or rectangle, and then if you cut it on the diagonal, which is dividing by 2, you would get back to what your sum is. So that's the visual idea of it, all right? And to prove it, works very similar. So base case, 1 equals 1 times 1 plus 1 over 2. And that is true, because this cancels. And yes, that's good. So now I'm going to assume 1 plus 2 dot, plus k equals k times k plus 1 over 2. And we show that 1 plus 2 plus ... plus k plus 1 equals k plus 1 times k plus 2. I'm just adding 1 to everything in there. So, just like the last few, I'm going to start here, and I'm going to show that I get this. So, let's just use that color. 1 plus 2 plus blah, 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 plus k plus 1 equals k times k plus 1 over 2 plus k plus 1, right? By, don't need that capitalized, by our assumption. And then just say something like note k times k plus 1 over 2 plus k plus 1 equals k times k plus 1 over 2 plus 2 times k plus 1 over 2, just getting common denominators, which is then k times k plus 1, I don't really have enough room there, k times k plus 1 over 2 plus 2 times k plus 1. And I can like factor, I got this and this, these common factors, and I can pull that out and get k plus 2 times k plus 1, right? And then that's all over 2. And that does it. I'm not going to, actually, I don't really have room to write it up nice and neat. But the idea is, then I would just say something like, this proves my inductive hypothesis, and thus this thing holds for all n in the naturals. So hopefully after seeing 3 of them, you kind of get the feel. Basically, there's always like a step where you use, here I'm just taking this first k naturals out, and I'm putting in this part, which is what I assumed it equals. And then there's always like some massaging with the algebra, and then you should get the thing that you want to get. And then it is good to always add like a conclusion kind of sentence, but I just don't have it. And that is induction in 20 minutes.